The broadcast is now starting. All attendees are in listen-only mode.
Good morning or near afternoon, depending on where you are. Presenting today is Kevin Stelzer. Thank you very much for everyone attending. We're going to have a great presentation. Kevin is a founding principal of Inform Architects, a practice that specializes in ultra energy efficient design in educational laboratory and retrofit building sectors. He has worked across Canada, the United States, the UAE, and Asia. He studied architecture at the University of Waterloo and studied building science at the University of Toronto. He is a licensed architect and a building science specialist. He has served on the CAGBC Energy and Engineering TAG on the UN SBCI Task Force, volunteered for the WGBC, and currently sits on the CAGBC Embodied Carbon Working Group. He was the recipient of the 2017 CAGBC Toronto Leadership Award. So Kevin, we're pleased to have you aboard, and I'm going to hand things over to you, and you can get your presentation rolling.
Thank you very much, Kevin. I really appreciate it. It's exciting to be here. This webinar format is new and exciting for me, but am very enthused and excited to talk about the Joyce Center, and especially within the context of laboratories in particular. And you know, this presentation will focus a little bit on why we think laboratories are special. And I guess I just want to start, if I might. I was the design principal in charge of this project while I was at B+H Architects. It was a joint venture project between McCallum Saylor and B+H Architects, and I worked with a pretty remarkable team. Joanne McCallum was the executive principal in charge from McCallum Saylor, and we worked with Steve Kemp, a national energy expert, perhaps even international expert in energy. Wonderful to work with, really important on this job. We're going to talk a lot about that. Steve Orchard was the chief mechanical designer from the Mitchell Partnership. Shaylee Patel did an amazing job on the electrical systems and our PV array, which we'll also talk about quite a bit. Tony Manicon designed the great structure from Manicon Partners. And, you know, this is just the tip of the iceberg, you know, very large team. Acoustics was done by RWDI, code by LNDG. And of course, we have to give thanks out to our amazing leader at Mohawk College at the time, the chief buildings officer, Tony Caputo. So I just wanted to, you know, give a shout out to that amazing team. And I'm just going to launch right into it here. I would love to talk about this project. You know, it's not really, I would think, a kind of a linear, it's not really a linear narrative. It's more of a, I guess, a constellation of ideas that really helped us try to move this project forward. When the design team got together initially, and Tony Caputo was like, you know, this building should be net zero energy. And at the time, you know, we could look at the, say, the Living Building Challenge as a certification system or a standard for net zero energy, but you know, it wasn't that common. It was a little bit controversial, like, what does net zero energy mean? So, you know, we just started talking about, like, you know, we have this amazing engine to the solar system. You know, how do we capture all that energy? In 45 minutes, enough solar energy hits the surface of the Earth to power our global economy for a year. So there's lots of energy out there. There's lots of renewable energy. We just need to, you know, shift our mindset, develop some new tools, re-engage some old tools to actually harness this this incredible power plant of the sun. William J. Mitchell, back at, you know, around the 2000s, wrote this amazing book called City of Bits, and this is important with respect to this project as a laboratory, because Bill Mitchell was talking about how cities and buildings will start to change when we have access to large amounts of information that we can manipulate sort of at our whimsy. So the idea is, you know, how do libraries change when, you know, so much virtual information is made available to us, and we can see how libraries are actually becoming even more important as social condensers. This idea that architecture can influence human behavior in a positive way. And so the idea of a library, instead of it being kind of this vault or archive of very special physical objects, it's a portal, it's an access point to immense amounts of information. But with that information, once it's retained or gathered, it needs to be socialized. We need to make sense of it. And then the actual place of the library is somewhere where we can do that. He also talks about labs as a very, very important typology moving into the future, even more than they have been, because what really is a laboratory? It's a source of innovation. It's a place where people innovate, they ideate, they look for what doesn't exist. So how do buildings contribute to that? Especially in the context of massive amounts of information, we need to, again, socialize that information. We need to create places that help people interact with each other in a really productive way. And we really tried to kind of engage some of those ideas in this project. This is a great book by Klaus Daniels. This was, again, written in 2000, but the idea here is that with massive amounts of information, or the access to lots of information, we can change the way in which we design. And he also purports that, we tend to sort of idealize or perhaps even fetishize high technology. It's a bit of a deus ex machina. What he's saying there is that we should really just pick the right technology. There's no high or low technology, there's really a light technology. And with our access to information and our processing power, we should be able to create buildings that are light, that have a light footprint. So I got this example from Ted Kessick at U of T. And when we kind of look back through history, we can see that buildings, we might look back and, with nostalgia, sort of look at the, this wigwam and say, isn't it a lovely sort of piece of historical, design? But actually, when we kind of dive into it, we can see that there's actually an incredible amount of building science that's at work here. If we look at the skin of the building, we can see that there's, 2 layers of these bent birches, and in the middle we have moss put in there. So it's, it's cavity construction. It's insulated. Somebody understands that, air insulates better than water. So if we have moss, full of little pockets of air, we're going to have good insulation. So that's quite sensitive and advanced. And then we line the outside of the cavity with imbricated birch bark, so that it actually naturally sheds the water. There's some building science there. I mean, we can look at the furnace. The fire at the center. It's wrapped with a thermal mass, so that as the embers burn down, the rocks can absorb the heat and we can be more comfortable through the middle of the night. And I love there's the birch bark supply tube. We'd call that an outdoor combustion kit now, but this idea that, the designer of this little building was aware that, combustion is far more efficient when you have access to fresh air. So there's a lot of building science built into this little building. And of course, if you wanted to move or, you didn't like it anymore, you could kind of leave it in place and it would decay. And probably all the parts of this building were probably sourced within 100 meters or 200 meters of the site. So actually quite advanced, I would say. And I think we need to sort of think about that. Klaus Daniels asks us to look at things with that sort of a more objective lens. In this case, on the right, we have the BRE headquarters in England. And then on the left, in northern Pakistan, very hot and humid, what do you need to do? You need to go up into higher into higher elevations to capture higher velocities of air so that you can, induce airflow through your buildings. Very similar concept to the BRE headquarters. So, independent of the time, there's no real high or low tech, there's the appropriate tech. I mean, of course, I think even the buildings on the left here are actually quite beautiful. There's a wonderful sort of vernacular motif going on. Some other ideas, again, I'm just collecting a few ideas before we get into the building here. Every sustainable designer needs to understand this sort of this pyramid. And the idea here is that, I'm just checking to see if there's a comment here. Oh, great. Okay, we're good. All sustainable designers need to understand this tier. Really, in the end, for contemporary buildings, there's no real 100% passive building. What we understand is that a very low energy building, a very healthy, high efficiency building has very high efficiency systems, but those high efficiency systems need a very, very robust passive strategy to support them. So the idea is that we look at the overall basic building design, the massing, essentially a smaller building uses in general less energy than a larger building. So if we can optimize the floor plans and the footprint of the building, that's better. Once we start getting into passive systems, the next tier, we start insulating the walls with very good thermal performance, very good windows. We optimize the amount of glazing we have, and we make the building very airtight. And then once we've done that, then we can, when there's parts of discomfort, we can use very optimized low intensity mechanical systems to support comfort. So the idea here is that, similar to Passive House certification, the principles that build that up, we're looking at the Joyce Center to stabilize the interior environment. So that gives us the best shot at controlling the loads and separating ourselves from the weather file as much as possible, and then we can have a very, very good, better chances at putting in very, very low energy systems. So that was an important idea to us. Understanding the weather file, climatology is our friend. I mean, there's no such thing as free energy in thermodynamics, but for the sake of building design, there's free energy, and understanding those latent energy flows is very, very important for us. So, looking at, this is for Vancouver, plotting out every hour of a typical year on the psychrometric chart, you get a sense of the total energy content of that air. And then what are some of the passive strategies we can use to address them? Very, very, in a very simple way, the four basic climate types. If we're right in, if we're kind of low and to the left, things are dry and cold. That's a cold climate. That's more like Toronto. If we move to the right, we get warmer temperatures, drier. We're closer to desert. If we go up on the psychrometric chart, we get into high temperatures and very high humidities, high enthalpy. That's a tropical climate type. But of course, right in the middle, right around the comfort zone, we get more of the temperate zone. It gives us an idea of some of the basic strategies that we can use. So it's something important to understand. I love this idea. This comes out of California. Loises and Ubenhold. They've designed this wonderful graphic output. What they've really done here is invert the typical design process. What we generally do is we try to use our best intuitions, best efforts, early analysis to structure a building and structure systems, and then we run it through an energy simulator and a weather file, and we spit out an energy intensity. Do we like that or we don't like that? What they do here is they've designed some special extensions to Energy Plus, where what they do is they're designing the building from a purely passive perspective, and then they count the hours of discomfort. And then what they try to do is change the passive measures to reduce those hours of discomfort. In the case here, this is from California, so they tend to overheat, but they're beautiful graphs. Wonderful way of describing, the hours of the day and the months of the year. When is the building uncomfortable? Can we change the basic fundament of the building from a passive perspective, the structure, the overhangs, the insulation, the glazing ratios, to reduce those hours of discomfort? And then when we run it, when we've exhausted all those passive measures, then we put in just the right active measures to satisfy comfort. So it's kind of an inversion, and I think it's a very beautiful representation of how to do energy modeling. But this is something that we were thinking about very, very much in the Joyce Center. How can we create a thermally autonomous building? We started early on by benchmarking the building against other buildings, other high-performance buildings, cold climate buildings. And we developed an energy budget. So, all projects have a financial budget, like a capital cost budget. We have a schedule we have to adhere to. That's common and understandable. But we also said, what, before we even do blocking and stacking, before we even do any architecture, and as an architect, that's a difficult thing to do, hold up the architecture. We'd like to jump in and start designing things. But what we said was, what's our energy budget? Break the systems down. For a laboratory, plug loads are hugely important. Ventilation loads are hugely important. Can we make allowances for those aspects within the energy model? And then, start picking very high performance systems to see if we can generate energy intensities, metrics that we think are high performance, And then can we balance them out with on-site renewables? And so this is the energy budget. And we started this right from the outset. We were very fascinated. We were very excited to participate in the Zero Carbon Framework as a pilot project for the CGBC. It wasn't around when we started the design projects. We actually started with a full net zero energy sort of mandate. As we'll show later, we installed 545 kilowatts of photovoltaics on in and around the building. But what we started to really discuss as the Zero Carbon Framework was coming out is really what we're really interested in. Clean energy is what we're really interested in. Is we want the building to be powered by clean energy. We don't want it to pollute. We want it to use the right amount of energy. We don't want it to just be focused on low energy, even though efficiency is important. We want to actually optimize the amount of energy we use. And I think the Zero Carbon Framework gives us that. It's a tool to help us do that. So we really like that that certification. It does demand a certain amount of efficiency. There's TEDI requirements within the Zero Carbon Framework, so it's an ultra efficient building. It cannot rely on fossil fuel consumption for power. And because it emphasizes low thermal energy demand intensity, low TEDIs, we have to control loads, use passive systems, and then when we do employ active systems, they're low density. And then of course, once we've done that, it's a high performance building with all the right metrics, the low energy intensities, the low TEDIs, the passive systems working in concert with the low intensity HVAC. We understand that power profile, and all power has a carbon footprint, and we understand, with the Ontario grid, that electricity is our kind of generally our best option for a low carbon approach. So we count up the carbon intensity of our usage, and then we offset it on site to clean that out. So it's super important that we get the this drive for solar energy, and just some kind of renderings and a photo of how it was important for the design team to express the fact that this building, the engine of the building, was solar. So that was important for us. I just want to explain the project a little bit. So there's a whole bunch of ideas, they're not really that well linked, and I apologize, but they just sort of, for us, form like I say, a constellation or a network of values that we tried to have the design respond to in a very, very direct way. This is the site. I think quite ironic, these suburban sites in the sort of 50s and 60s. This is the Fennel campus at Mohawk College. It started off as a fairly suburban site, annular ring road, and a fairly pastoral relationship with interlocked buildings, lots of lawns, lots of views. But over time, actually the density is quite significant. So, our building is kind of nestled in here. This just shows us how we kind of developed the blocking and stacking. There was a few mandates we had to, maintain. The building had to connect to the existing engineering block on the north, and it was snuggled in between a very important building on campus, the student pub, and then the new School of Business on the east side. So maintaining fire distances from those buildings. We had a floor plate. We needed 5 stories to connect to the 5-story E-wing, which was the existing engineering block. And then, of course, that 5-story block, it included the sort of desire line to the entrance of the School of Business. So we decided to separate the 2 volumes and create this atrium so that there was, we were being neighborly to that building, so that there was you could see through the building, and then there's an ease of access. We also took the front volume. We did notice there's an informal boulevard. The kind of ceremonial boulevard for the campus was out front there, and so we swung the block around a little bit to kind of honor that ceremonial boulevard. And the college was very interested in having a green roof, so we slid on a little green roof. So this just shows us that there, in the end, even though we were trying to kind of control the overall building massing for an efficient low energy building, we didn't have a lot of choice in doing that because of basic parameters, basic exigencies of the site and program. And what we ended up with was a fairly major western facade, which of course is not super good. So we had to wrestle with that. just wanted to show the plans a little bit. This is the ground floor plan. So it is a teaching and research lab. So even though we're very focused on energy, energy isn't the it still has to be a building that thrills the occupants and is a super, super highly functional building. So teaching and learning buildings need to socialize education, as I sort of mentioned earlier about laboratories need to enhance innovation and help people collaborate. Similarly, teaching and learning buildings need to provide the social spaces and the spaces of interaction so that education can be accelerated. So I say that to suggest that we had 2 high-capacity classrooms, and we oriented them around a major public atrium, so that these classrooms, the backside of these classrooms, had large doors that could open up, and when they weren't in their kind of typical lecture mode, these classrooms could then kind of flow out and actually participate and engage, a kind of a crush space, a social space. These the next level up, level 1, which was the major connecting level to the E-wing, which is on the bottom portion of the plan. There was a large like information commons area, and then we can see the upper story of the 200-person classroom there, all framed around this atrium at the top. But above that, level 2 and level 3 and level 4 were laboratories, and some of the laboratories were still in the process of programming. So what we tried to do here was we tried to develop kind of an armature, almost a modular lab. So all the services were built into a spine, and then the idea is that the labs get stacked up on top of each other, and then there's a lot of flexibility in their programming as the building opens. Again, coming back to the teaching and learning here, we see the sort of axle showing the large classroom connecting with the atrium here. What's kind of important with this image was that there was a hybrid kind of venue design. It's a high capacity classroom, but there's also this idea that you get this ability to take tables that can be reconfigured. You can not only do lectures, you can do labs and tutorials in the space. The space can also operate as a workshop and a studio space when it's not in its formal lecture mode. So there's a lot of flexibility here. And again, the large doors opening up to the social space is super important. This slide is intended to kind of reinforce how social the central atrium is. At B+H, when we were there, we participated in a bit of research, and this is a little bit of a story about how effective the laboratories can be. We participated in a study that was performed by Vlad out of Boston, and they gathered something like 1,500 labs throughout North America, and then they tried to evaluate how effective the architecture was in promoting innovation and research. And I mean, how do you do that? But they selected a metric of number of papers produced per researcher per square meter. They amalgamated all the data, plotted it out, and they found there was sort of three nexus, three sort of gravities. They discovered that laboratories that were 3 stories or less were more productive. People who walked up and down stairs, who could interact with people on different floors, tended to be more productive. They also discovered that buildings that were more transparent were on the whole more productive. So the idea is that people seeing other people being productive, there's an acceleration of their productivity as well. And then there's also this idea of like, investing in, creating, or kind of expressing and generating curiosity. But the highest, or so the greatest source of productivity gravitated around labs that had cafes. And I can understand this because, in the morning I need my coffee. That's just absolutely essential. And, in that mode of sort of, dragging your butt into the into the cafe, sitting down, having your coffee, which I really need, you just start interfacing with people. You start discussing things. You know, people start talking about, you know, their challenges or their successes. You start talking about your challenges and successes, and suddenly, you know, you get these interfaces. You get the socialization of your research, and innovation comes out of that. So it's very, very important that labs have cafes. So we recommended that the Joyce Center have a cafe, and they do. So we're happy about that. Now I want to talk a little bit about the passive strategies, and then I'm going to talk a little bit about the active strategies and sort of how they work together. Excuse me. So, you know, the sun is hugely important on this building, not only for generating on-site electricity, but also, you know, the solar loads. We had to understand that, so we modeled that extensively. Daylighting is, you know, as far as I'm concerned, low-hanging fruit, as they say. If there's light to be harvested, we should do that. There's no reason why artificial lighting has to work if we don't need it. So we modeled for daylighting. You know, as we tried to shade the facade, this is more an architectural thing, I guess. You know, we love our solar shading, and we love our parametric modeling, and you know, we have a series of aluminum shades, vertical shades on the building, because we have you know, a very strong east and west exposure. And to help mitigate some of that solar load, we did these vertical shades. But we tried to look at, you know, how can we ornament them? How can we perforate them in this sort of interesting pattern? And that was something that compelled us a little bit. Just wanted to show that, you know, some of the research behind the scenes. When we look at the enclosure, it's again, we wanted to isolate, we wanted to stabilize the interior environment so that we could control the loads. So just looking at that a little bit, you know, we wanted to have, you know, controlled glazing. Just put in the right amount of glazing that we need. Put in daylight glazing to push that available daylight deep into the floor plate. But then we wanted a very, very highly insulated, you know, non-vision wall assembly. What ended up happening here, the story behind this slide is that Elliston, who was the construction manager on the project, and I thought did an absolutely fabulous job. They came to us and said, listen, our original design was, you know, more of a window assembly with a highly insulated, you know, opaque assembly above and below. We wanted the glass to be very flush with the opaque assembly, so we had this nice taut appearance. Anyway, Elliston asked, listen, you know, our schedule is very, very tight because we had funding deadlines to meet, and because it's a lab and there's a lot of work to fit out the interior, can we do this in curtain wall to accelerate the schedule? And our initial response was like, you know, that's just not feasible. Curtain wall doesn't have the performance. We get too much flanking through the aluminum. But they asked us really nicely, and we said, okay, well, we'll look at it. And actually, we started to look very closely at some of the highest performing curtain wall sections that we could get a hold of. We started separating the mullions from one another to help prevent thermal flanking. This slide is intended to indicate that, you know, one of the things that we discover as we start designing higher and higher performance enclosure systems, we're starting to discover that the smaller and the smaller holes or thermal continuities become a much larger problem, become a bigger piece of the pie. So even as we put in high performance glazing, you know, high performance units, triple glazed units with, you know, really good thermal breaks and so on and so forth, we get a really large flanking effect where the, you know, the heat, like electricity, just finds, you know, the shortest circuit to the ground, you know, shortest circuit to the cold, and we lose a lot of heat around there. So it was this flanking effect that we were very interested in. So we started modeling a system where we could separate the various curtain wall systems with structural rubber, so there wasn't this flanking effect. And then what we said is, without this flanking effect, we'll actually insulate in behind the spandrel with a foam insulation assembly, and so that we can start getting our effective R20 opaque assemblies, even though it's curtain wall on the outside, and we'll get our effective R7-ish, very high performance triple glazed vision assembly windows. And then the system will work together and meet our targets. And that's what started happening. Right? We started doing some 3D modeling to make sure that we weren't losing too much heat around the anchors. And then we worked with some industry partners, in this case Schuco. So Schuco said, well, we have a system here that we can actually connect with structural rubber. You can see that, you know, the two halves of a unitized current wall system here are actually held in place by structural rubber. So the heat flow from, you know, a vision panel to, say, a highly insulated opaque assembly next to it is highly inhibited, and this was the key. So here we could actually propose an effective little over R20 imperial opaque assembly with our high performance triple glazing windows to meet our targets. And we were quite proud of this, and this is quite innovative, I think. And that was the system that was put in place. Now I want to talk a little bit about the going back to our energy budget. Now we want to talk a little bit about the active system. So, you know, we worked really hard to try and control the loads, keep the heat in the building, reflect out the western sunlight, and now we can look at, you know, highly optimized heating and cooling and very, very high quality ventilation. So, you know, all good sustainable designers, in my opinion, separate out the systems so that you're ventilating when you need to ventilate, you're heating when you need to heat, and you're cooling when you need to cool. So we're not stacking them up and then enlarging the systems bigger than they need to be. We ended up selecting. Let me just check the time here, make sure I'm doing okay. I think I'm doing okay. We selected a ground source heat pump system, but a VRF system, which we thought was very effective. VRF, we selected VRF because of the very superior latent heat recovery that happens through the refrigerant loop. So the idea here is that because it has a very strong east and west exposure, we have differential loading on the building. So the idea is that in the morning when we're overheating, we can actually take that heat and deposit in other zones on the west where we need the heat, and then vice versa. When we have a tendency to overheat in the west with the western sun, we can take that heat, and then the heat actually moves through the system into the zones that need the heating. So we have very, very good heat recovery. We have very, very stable heat source for the winter through the ground, and that worked out really, really well. Here's just an image to kind of support that. This is our mechanical room on the top. We have our dedicated outdoor unit with heat recovery, energy heat recovery. And then we can see to the lower right there our bank of 24 VRF water source heat pumps. Again, so the water-cooled geothermal VRF system was the system of choice, very, very high efficiency. And again, this idea that because we have a whole array of, you know, about 24 of them, they each have multiple speeds. So we have this amazing kind of granularity of revving up and revving down. We can spool up and we can spool down to meet our load, and that gives us great efficiency. And also we have this ability to move heat around the building, and the compressors work very, very, very lightly to do that. So some zones can be in heating and some zones can be in simultaneous cooling, and that's very efficient, especially in our building here. We also wanted to mention that, you know, in the entrances, you know, we have sort of a higher loading there. We have some force flow heaters. So we had booster pumps that produced higher temperature water, but they were still heat pump booster pumps that satisfied that load. Very high performance ventilation system. You know, it smells the CO2 in the air and then it ramps up from like 10% to 100%. And the idea here is that we just satisfy the load when we need it, and we can get very good heat recovery through our enthalpy heat wheel here. Very efficient. We also, the college was very interested in solar thermal, just understanding how it worked. So we did have a small domestic hot water load, and we satisfied that with a solar thermal array. Just looking a little bit at the energy simulation. Some of the outputs here, we can see that, you know, a majority of our load is ventilation, which is what we expected. So we're controlling the skin losses, and we're focusing on the loads that we can, quote unquote, control a little more. So the idea is that, I mean, we can't control occupancy. We can't, you know, if occupants want to leave the windows open, that's their choice. But if people operate the building responsibly, certainly like Mohawk College has and is, we really wanted to focus on a demand response. So the building will respond to the demand. It will provide just the right, the optimized energy to fulfill the load. And the idea is if the building's not occupied, then it can just, it can rest, it can spool down, and it can rest, and we don't have to spend that energy. This just looks at a whole series. Steve Kemp, our energy engineer, certainly had his work cut out for him. You can see number 20. We went probably a few more than that. The energy model was run many, many times as we looked at various updates and tweaks and modifications. In the end, we predicted an EUI of about 71.5, which is pretty low energy for a Canadian cold climate building. If we index this to say a typical office building in Canada right now, it would be about 335. So I think we were doing pretty good. Now, once we've designed, the low energy building, the highly efficient building, we still need to pair it with on-site renewables to quote unquote clean out that energy or offset that carbon intensity. Now, one of the advantages of working on a campus, now this is a 5-story building. We didn't have the footprint to generate all of our renewables within the footprint of our building. But working on a campus, we had the great advantage where there was a lot of other roofs that we could use to do that, and that's what ended up happening. We needed about, so the building is very roughly, well, it's 96,000 square feet, and we needed about 32 or 34,000 square feet of PVs to generate the 545 kilowatts to do the net zero energy. These are just some images there. It's very important for us to have this, this showcase element to express the fact that we were collecting all the solar energy. You can see Alice down there as the construction manager. Again, they did a great job. Some more images here showing the PV decks, and we can see some of the adjacent buildings there. So this was the final array, the full array. So on the upper left is the Joyce Center. So its roof is full of PV. And what we did for the upper two decks there, we angled them in order to increase the density, so we could get a few more panels in there for the area. But then there's a bunch of other buildings here that had the capacity. We did structural analysis to determine if they had the capacity, and we did a ballasted array on those buildings. I'm just checking the time here. I think we're almost done. We didn't have a huge domestic hot water load, but the load we did have was satisfied by this quite small array here. Solar thermal. These are Viessmann flat plate collectors. Quite efficient, over 80% efficient. So they translate the solar energy very efficiently into thermal. So we didn't need a huge array there. So I wanted to talk a little bit about, so that we had the building certified zero carbon, a design certification, and that was just as the building was being commissioned. And then the Joyce Center was the first building to also have the performance certification. So for a year later, the building was measured and verified, and the life cycle assessment was kind of calibrated, and we now know how the building is performing. As it turns out, we probably over-specified the scheduling of the facility a little bit. The college wanted to run nighttime classes and some summertime classes, maybe a conference or two, and that didn't happen. So the occupancy was a bit less than we expected. So our initial predictions of an EUI of 71 or 72, it actually came in just shy of 60. So it's a pretty efficient building, and that was certified over a year, and then we got the performance certification, and that was super exciting. Yeah, measurement verification was always very, very important to the design team and Tony Capito. So, you know, the kind of the infrastructure and technologies were built in there, but also the protocols to extract the information. And like everything in life, you know, you learn lots as real projects roll out. It's never, you know, theory is one thing and practice is another. And, you know, it's our jobs to, you know, as best we can synchronize those two things. So one of the things we started to discover, we worked with Daikin. Daikin were the suppliers to the VRF system. It's difficult for them to know. They know, electrically they know exactly what's going on. They know that, you know, the compressors are working at whatever speeds they're working at. They're all variable speed inverter compressors. All the fans, we know the power they're using. But we're not as certain as to the thermal, you know, how much heat is moving through the refrigerant. And Daikin actually worked with the college to develop a proprietary software where they could actually simulate to a very close degree how much thermal energy was running between the compressor and the various fan coils. So that was kind of interesting. So that information could be gathered. But you know, there's all sorts of other things. You know, in the design there was 48 electrical submeters, some heat flow meters, and water meters. But again, you know, syncing those values up to the VRF heat output was a challenge that had to be worked out. This is just sort of some of the highlights over the first year of operation. So it was from September 15th, 2018 to September 15th, 2019. So all the PV generation was measured. Some of the submeters didn't come in totally calibrated. They had to be kind of tweaked. The top floor was not quite outfitted, so we had to sort of index a partial occupancy there. So the calibrated energy model had to take that into consideration. And some of the lighting controls failed and had to be replaced. So we had to look at that. And then there was the ongoing understanding of how the building works relative to the weather file. It was actually quite independent of the weather file, very stable interior environment. So, you know, optimizing the temperature setbacks was something that had to be looked at closely. So, as it turns out, we simulated the building using maybe 600,000 kilowatt hours per year, and it came in considerably less, about 82% of that. So we're actually net positive, which I think was because it's you know, it's just a good story. This is just showing us how Steve Kemp tried to you know, calibrate the model, looking at the estimated PV production, looking at the estimated consumption of the building versus what really happened, and there had to be a bit of interpolation that went on in there to calibrate the model. The building had an on-site weather station, so you know, the you know, an advanced microclimate model was produced, calibrated. Yeah, and then the kind of troubleshooting that went on. It was quite a interesting exercise unto itself. And one of the things I think is that distinguishes Mohawk was they were very, very enthusiastic and engaged in how this building was intended to operate, how it did operate. They actually have a course that they've set up in one of these labs in the building where the students can operate the building for a portion of the year, so they can understand how important operations are to the actual success of the building. And then we understand that too. It doesn't matter to what level or to what sophistication you design to. If the building isn't operated with care and attention, it's all for naught. So, you know, Mohawk College was very, very engaged, and I was really pleased and totally privileged to, you know, deliver some educational sort of workshops and presentations to the student body to, you know, engage with them. You know, there's a lot of learning going on both ways, but, you know, giving them an idea of like what, you know, some of the ideas that compelled us and where it ended up, and that was very charming and satisfying. Then these are just some of the images of the project under construction, because I want to identify some lessons learned. Now, we did a whole building thermal conductivity analysis, and I guess you know, I'm feeling a little coy here because, you know, I'm advocating very, very high performance thermal enclosure, and of course I penetrate it with all sorts of assemblies, left, right, and center. And I just wanted to point out that all the structural penetrations through this enclosure were thermally isolated with either structural foam or structural plastic. We can see here these tall sort of steel trees. At their base, you can see how thick our roof assembly is here. At their base, they're all isolated with structural plastic. This stuff was Fabrica, so it worked really well, and it satisfied our energy load, but it was a lot of work. And I think somebody like myself would probably think about this a little more intelligently if I were to do it again. Not unless, I mean, fun, but also, a lot of work. And these are just some images of the final product. And this is our central social space. And this is the Lightwell atrium that moves between the new School of Business and the parking area. And this is just another image from the west. And I want to thank you very much. That's the end of the formal portion of the talk. I hope the timing was okay. Thanks very much.
Thank you very much, Kevin. It was a great presentation.
You're kind. Thank you.
What I'm going to do, there's a few questions, so we'll go through those. And perhaps if you have access to the chat window, if you could provide your contact information too.
Oh my goodness, I should have put that on the final slide. Yes. How do I do that? How do I type them in? I'll put my Kevin. Can everybody see this? Kevin Stelzer at Inform Architects. If I could type.
That's right.
I see Kevin.Stelzer at informarchitects.com. That's my. Does everybody see that?
If you might need to use. There's on the little toolbar. There's a chat, and you can.
Yeah, I put it in there. Yeah.
You can send it to the entire audience. And let me check. Yes, it popped up. I'm sorry, I had to scroll down a bit. So perfect. Excellent. So we'll jump to some questions here. Kevin Humaniuk had some questions. The first one is, can you comment on what you see as the major challenges in delivering the project?
I would, so that's a deep question, Kevin. That's a deep question. Okay. So I would say that the largest, for me, the most significant challenge was not technical. It was cultural. So on the procurement side, there's a difficulty both on on the delivery of the design and on the delivery of the construction. There's a culture of, I need to provide my services for the lowest cost. And I mean, that's understandable. It's public money. We need to compete for it. Everybody needs to optimize their financial resources. But the idea is that, when you ask for the lowest price, are you getting the optimized service? And a lot of the service providers, it was challenging for them to to understand the design to the level that is required is a challenge unto itself. And so if the services are being procured in a standard way, then you kind of get standard products. So that sometimes it was tough to get the trades to understand that, to give a concrete example. I'm really orbiting this question, and I apologize. But the idea is, the trade will come in and they'll be like, what, I know they want these kind of lights. This is just this is a hypothetical example, not a concrete example, hypothetical. I'm gonna bid on the job. I'm gonna put the low price on there. I'm gonna say that I'm gonna carry the lights, but on my shelf I got all these amazing lights, and I'll just sub it out with the client saying, I'll give you $10,000 back, and we can just use these lights. And typically that works. For this project, absolutely not. This is I would say the problem or the challenge with integrated design is that everything changes the gravity of the project, right? So you bring all these parts together and you have a whole, but when you start pulling the parts together, they all move a little bit, right? So it was very hard to do substitutions. It was very hard to do, everything had to kind of come together. So if anybody was like cutting corners or assuming that they could, not put the high efficiency, controllers in, then it was a problem. Or, oh yeah, I was going to put in the lighting controls. This is what I was mentioning about the lighting controls. Some of the lighting controls came in late, so those lights weren't working according to the energy model. So there was a little spike in a zone for lighting where they didn't. Oh, I was going to put them in. I'm like, well, no, you got to put them in now. Like, you're upsetting the balance. So that was a challenge, right? And I mean, I'm very empathetic to everybody involved, because how do you ask for somebody? I want a regular price, but I want extraordinary performance.
Yeah, I see what you're saying. You pull one string, and there's X amount of other strings that get pulled and tug on other things. So the interconnectivity of this particular approach can be challenging. So there's a few more questions. So can you provide some more information on the type of research labs in the building? Are they heavy in requirements for ventilation equipment, like such as fume hoods?
No fume hoods. It was a dry lab. Yeah. So there was like some computer labs. So there may be a heating load there. There were like electronics labs, photovoltaics labs. Yeah, there wasn't any fume hoods. Yeah.
Another question: were there any compromises that the team had to make that you would change if you had to repeat the process? So perhaps this kind of ties into a few of your comments on the first question. So I guess, was there anything that there? It seemed to me that the way you explained it, there's a lot of interconnectivity with impacting one aspect that would tug on a lot of strings elsewhere. Was there anything that you kind of dialed back on, and perhaps you did comment on that at the end of the presentation? Is that where you would kind of direct this?
But I mean, I really want to very earnestly respond to these types of questions. But one of the things I just want to say is that the team didn't look at compromise, and I totally understand where it's coming from, and I want to be very earnest here. If we're looking for a crystalline result, then you're always compromising. So what we try to do is engage in a process where the outcome wasn't exactly fixed, or we just believed in the process. We were going to get there, but how are we going to get there? We're not quite sure. So under that aegis of that sort of thought process, I would say that we didn't compromise. I mean, one of the real challenges here was the funding mechanisms. We had to, from procurement of the designer to commissioning, had to be 3 years. So we were making a lot of decisions to satisfy the funding. Now you could say, just give me the money and I'll do whatever I want, but then you make different decisions. So we didn't question the funding mechanisms. We just said that money is available if, if you.
Some flexibility was going to be needed along the way, and it seems like you.
Oh, absolutely. Yeah. I mean, as a designer, you're really close to the project. So I mean, I brought up this image here, and I'm actually kind of. So you can see that there's a kind of a black generator on the roof. To the lower half. Can you see the image? Can you see the image here?
I can't see. No, I didn't recognize the generator before, but pointed it out.
Yeah. So I'm just saying this is a real sore spot for me, but it didn't come in on time, so we actually had to move it outside, and when it came in, it was craned into place, and you just like get on with life, right? But it's like, did I want it there? No, are you crazy?
No,
so I mean, but I don't really think it's just like I mean, in the end, these funding mechanisms work to get things going. Half the time you're given extensions. Was this project given an extension? Probably. Could we have banked on that extension and then kept the building open and then get the generator put in there? Who knows? I don't know. I mean, I think it worked. It's you just go with it, right? You try your best. And I mean, I was thrilled with the team. It was a great team. It was an amazing client. Sometimes speed is your friend, because you get things done and make decisions. And we learned a lot on the way. So for me, the procurement was tough, because Ellis Don was great. Trying to get it was very busy at the time. The funding was activating a lot of trade involvement all over the place. So getting a lot of really good bids was sometimes tough on the quick schedule. You might have like 2 or 3 bids instead of 7 or 8.
Right.
So that would probably have an impact, if you had a bit more time. So, but the team tried to just sort of very progressively and like I say, earnestly engage the constructor and the mandate of the the client to get to the best outcome possible.
Great. Well, it sounded like it was a really good team effort overall.
Absolutely.
So one more question we have: how involved did the architectural team need to be in driving the engineering for the project? Two-part question, perhaps. And second part: how was project coordination used by the design team?
So it was an absolute pre-design mandate that the engineering was absolutely integrated, and it was an integrated design process. And one of the things that we did was bring the engineering up to the client level, so that the client isn't just seeing the architect say, well, VRF is the right solution. They're seeing 4 or 5 engineers as well nodding their heads at the same time. And then that builds confidence, it builds authority, it builds a collective understanding of the basis of design, so that as things are moving forward, it's not just one entity or one force sort of pushing the square peg through the round hole. It was a team that understood all the outcomes, right, and in their various efforts could work through them. So there was a bit of a design assist in the PV design. So we had a design for the photovoltaics, but we had to be quite flexible, and what panels were selected, where they went, how they were wired. It's it's a bit of a, it's not a black science, but it's a bit of an art to how to wire these things so you maintain the voltage, so that the minute there's bird poops on one panel, the entire array, the efficiency of the array isn't adversely affected. So working with the trades on stuff like that was really, really important. On the VRF side too, optimizing the routing of the refrigerant piping was very, very important, because what we discovered, this building about 100,000 feet was probably the largest we could get for VRF. We wouldn't go larger than this for VRF, because the refrigerant lines were sort of topped out.
Yeah.
So making sure that was covered, we had to work very, very closely with the trades and HTS as the supplier, with TMP. So it was quite integrated, and the integrate in terms of the coordination, you really just have to sort of mandate the targets. That's why we set out with the energy budget. So how do we meet those energy budgets? Like, as long as we're meeting them, I'll do my part. I'll design the enclosure to what we've discovered is that if you have an overall whole building conductivity, thermal resistance of about imperial R10, R11, you're in our climate zone, you're on your way to a very, very good performance. Our TEDI on this was around 20, 19 or 20. Yeah.
All right.
I hope that answered the question.
Great responses. It was very helpful. And the comment there, fantastic information, and very helpful to hear the responses. Thank you. So that's it for questions, and we're basically at the top of the hour. So once again, Kevin, thank you very much for your presentation. It was excellent. This presentation will be available on the SLCan YouTube channel as well. So with that, we're going to close things out, and everyone have a great day.
Thank you so much. I really appreciate it.